Hello, let's begin with chapter 8, Viscous flow in pipes. We all know what exactly flow in pipes is. It's such simply a pipe flow. However, in chapter 3, we learn Bernoulli's equation and we assume that viscosity of the fluid is negligible. We don't consider viscosity of the fluid in chapter 3. We use Bernoulli's equation in its perfect form. However, life is not so perfect. Every fluid will have some viscosity, some thickness, and that's why the title of this chapter is Viscous flow in pipes. The word viscous means stickiness of the fluid or thickness of the fluid. In chapter 3 we did not consider that stickiness or thickness of the fluid, but in chapter 8 we are going to consider that viscosity of the fluid, and then we are going to modify our Bernoulli's equation, and then we are going to understand we are going to use that for practical application. There are two kinds of flows. One is closed channel flow, which is a pipe flow, and another is open channel flow. Now, in closed channel flow, the pressure changes as the length increases. So here you start with very high pressure, and then because of the friction between fluid and the pipe and internal resistance of the fluid, you are going to lose some pressure, and then you are going to end up with relatively lower pressure at point 2. So that's your pipe flow. You are going to get always lower pressure in the end. So high pressure here, low pressure here. In case of open channel flow, that's not the case. Open channel flow, here pressure is same at point 1 and point 2. Open channel is open to atmosphere. Normally the pressure here and here will be atmospheric pressure. There is an entirely different chapter for open channel flow. We are not going to take a look at this chapter right now. Today we will learn more about this pipe flow or closed channel flow, and we will try to understand the viscosity and thickness and friction in that fluid. So pipe flow is extremely important in our lives. Water distribution channel, otherwise water distribution in our homes, or oil pipeline, or natural system of pipes, that's veins in our body, hydraulic fluids in various components of a vehicle, or air conditioner, that HVAC system. All these principles are different, but the fluid mechanics principle governing this fluid motion are common. So here we have a fluid we are transporting here from this point to this point, and then it will go through various sections. We have pipes, we have elbows, we have pumps, we have T's, we have valves, and throughout this, everywhere the fluid mechanics principles are same. Whether it doesn't matter what application that you are using, the fluid mechanics principles are same, and then we have to use those fluid mechanics principles to design this kind of systems. Now every time the fluid flow is there will be some friction, there will be some energy losses, and we have to learn those energy losses in order to design a better and more efficient system, and for that fluid mechanics principles will help us. This pipe flow begins with this guy, Osborne Reynolds. In 1883, Osborne Reynolds was conducting some experiments. Mostly these experiments consist of lots of fluids, mostly water, and some transparent tubes with different diameter. And then what he did in these experiments, that he injected a dye in the fluid flow and he observed the pattern. And that's pretty much he did. There's nothing much into it, but it was very simple and very important experiment. So injected a dye, and then he saw the pattern at various different velocities, different diameters, different flow rates. And then he saw how the flow looks, whether it is nice, perfectly smooth flow or very turbulent flow. And then he came up with an equation. He said that there will be something called Reynolds number. Reynolds number is dimensionless entity, it does not have dimension. Reynolds number is density, velocity, gravity. Density, velocity, diameter by mu. And then he said that if you do this calculation, you have some fluid with some viscosity and density. The fluid is moving, has some velocity, and there will be some diameter for the pipe. If you do these calculations for any flow, and then if Reynolds number is very low, then he said that the flow will be nice and smooth. If Reynolds number is very high, he said that flow will be turbulent. And that's what his observation is. So here are some numbers. So this is our equation, rho v d by mu, that's your Reynolds number. He said that if the flow is very smooth, if the Reynolds number is less than 2100, if this calculation, this number is less than 2100, you will see this kind of pattern. It's very nice smooth flow. You call it laminar flow. Then he said that if the flow or if Reynolds number is more than 4000, then the flow will be like this. It will be very turbulent. And then somewhere in between 2100 to 4000, you will get transitional flow, which is not exactly laminar, not exactly turbulent, somewhere in between. And that was his observation. It is very simple observation, but we almost 120-30 years later today, we still use this idea of Reynolds number to solve the problems. So Reynolds number, if you see here, normally density and viscosity of the fluid will stay constant if you are using the same experiments, if we are using same fluid. Diameter of the pipe is also constant because it's a geometry. Only thing is velocity could change. So you can imagine if where there is a high velocity, there will be high Reynolds number. If there is a low velocity, there will be low Reynolds number. So mostly that turbulence is depend on velocity. And we did this experiment with water hose, or we have some older faucet at our house, we can do that. So this one is one of the faucet. If it is velocity is very low, you can see nice laminar flow, transparent flow, very smooth flow. If your faucet is fully open, velocity is very high, then you can see the turbulence here. So that's your laminar flow, transient flow, and turbulent flow. You can do this experiment with garden hose at your house. So these are the numbers. He said that doesn't matter what flow is, below 2100 smooth flow, call it laminar. If it is more than 4000, call it a turbulent flow. And that's the importance of Reynolds number. Now here we will do a problem, and if you are in the class, if you attended the class, you did this problem in the class. So in this problem, what we have to do is that we have to fill up this glass with hot water and then cold water. And we have to find out how much time required to fill up this glass. We have some water faucet, we have some volume for the glass. Here volume for the glass is 12 ounce glass, so 354 into 10 to the power minus 6 meter cube. That's the volume for the glass. And then we have to find out how much time is going to take to fill up this glass. First we are going to use cold water at 10 degrees Celsius. Then we are going to use hot water at 60 degrees Celsius, and then we are going to try to find the time. Now it says that the Reynolds number for this one is somewhere in between boundary of laminar and transient. It means that Reynolds number is 2100. That's your boundary of laminar and transient. So if Reynolds number is 2100 for this water flow, we have to find out how much time required to fill up this glass. So the way we do this problem is that from Reynolds number we calculate velocity. So we know 2100, we know density, we know viscosity, we know diameter of the pipe. Diameter pipe is 2 centimeters, that's 0.02 meters. Make sure that you convert it in meters. So you use that and you should be able to calculate velocity. Once you have velocity, you should be able to calculate flow rate. And once you flow rate, you know the volume, you should be able to calculate time. Flow rate is amount of water coming per unit second. So you have already how much volume is going to fill, and based on that you should be able to calculate the time required, and that's the problem. And then if you do this problem at home, you can pause it, you can try to calculate it. So here I will do this calculation for you. If you do this calculation, you get first you get velocity for the cold water is 0.136, and then you can calculate flow rate and you can calculate time. The time here is around 8.2 seconds for cold water. Once you are done with cold water, you do same calculation with hot water, and then you will get 23 seconds. So it means that for same volume, cold water is going to take less time and hot water will take more time. So here in this graph you can see there we have temperature, we have temperature here on x-axis, when we have time required on y-axis. So here it doesn't matter what the Reynolds number is, it doesn't matter whether it's laminar flow or turbulent flow. If it is cold water, then it's going to take less time. If it is hot water, it's going to take more time. So here, if 200 degree Fahrenheit is the water, it's going to take around 38 to 40 seconds for laminar flow. For turbulent, it's going to take 20 seconds. If it is cold water, let's say 50 Fahrenheit or 10 degrees Celsius, is going to take less time. So that's what we can see. Hot water takes more time, cold water takes less time. Now, we will learn more details about this fluid flow or pipe flow. This is entrance region and fully developed flow. So let's assume that I have a large tank, and then from this tank the water or our fluid is entering in the pipe. Now what happens here? Initially, when the fluid is entering in the pipe, we have velocity profile is almost equal. The reason it is equal is that there is no friction yet. So initially the velocity profile will be always same, but as the flow progresses here, because of the friction here, the velocity profile will be different. Now the velocity here will be almost zero here, and then you will get higher velocity at the center, and then you will get this kind of velocity profile here. And then as flow progresses further, there will be a point where you will get this semicircular profile. Here we have very high velocity, and here we have almost zero velocity. So that's your 0 meter per second. So now that happens because of the friction here and friction here. And when that happens, when you get this fully semicircular flow, you can call it as fully developed flow after this point. So from here to here we have a fully developed flow. Before that we have a developing flow or entrance region flow. So that's how it works. Initially you have nice velocity profile which is same everywhere. This is a straight velocity profile, and then the profile changes, and then you will end up with nice semicircular profile which is a fully developed flow. And then flow will continue to stay fully developed up to the point which meets an obstruction, and it will become again a developing flow, and then after a certain point it will become a fully developed flow. So if you are studying this kind of pipe problems, this entrance region flow is an area of interest. We want to know how much time required or how much length is going to be there so that flow will become fully developed. So this is called entrance length, LE. We want to know that how much it is. So that entrance length is a function of Reynolds number. And then if its Reynolds number is less than 2100, let's say it's nice and smooth flow, it's very low, and you can use this formula. Entrance length by diameter of the pipe is equal to 0.06 Reynolds number. If it is a laminar flow, if it is a turbulent flow, you can use this formula. Reynolds number by diameter is equal to 4.4 Re 1 by 6. Now if you do whole lot of experiments, you will come up with this kind of formula. So it's already there, we can use it, and we can try to use, we can find out the entrance region length, a length after which the flow will become fully developed. So let's do a problem. Now in this problem, what we have is water enters in the lead pipe. So this one is a lead pipe. Water is entering in this section. Initially nice velocity profile we have, a straight velocity profile we have. This is your developing flow, and then you will get here developed flow. And we want to find out this entrance length for this lead pipe for this diameter. Diameter is 10 centimeter, which is 0.1 meters. Length, total length is 8 meters for the pipe. Volume flow rate is given in gallon per minute, so we have to convert that into meter cube per second. Then we have to calculate entrance length, and then we have to answer, does the flow become fully developed? So if entrance length is more than 8 meters, flow does not become fully developed. If it is less than 8 meters, we can say okay, the flow will become fully developed. So first we have two equations. We need to know whether this flow is laminar or turbulent, and for that we need to know Reynolds number. If we want to know Reynolds number is nothing but rho Vd by mu. Now we have density and viscosity here. We have diameter, we don't have velocity. Instead of velocity, we have flow rate. So we have to find from the flow rate, we have to find out what is velocity. The flow rate is given in gallon per minute. So first of all, we have to convert that flow rate into meter cube per second. So this is the conversion. 1 gallon is 0.038 meter cube. Multiply that with 15.85, you will get meter cube per minute divided by 60, and then you will get meter cube per second flow rate. Once you have flow rate, which is around 0.001 meter cube per second, you can calculate velocity. Velocity is equal to V is equal to Q by A. You will get velocity around 0.127. Once you have velocity, you should be able to get Reynolds number. Now Reynolds number is around 12,600, which is very high, which is a turbulent flow. It means that you are going to use this equation. You are going to use this equation, put the Reynolds number here, 12,600 here, and then do your calculation, and you should get entrance length, which is around 2.12 meters. So flow will become fully developed after 2.12 meters. The total length of the pipe is 8 meters. It means the answer is that does the flow become fully developed? Yes, flow does become fully developed after 2.12 meters. So that's your answer, and that's how you can calculate this entrance region length. It is very simple. Now let's move on to the most important part of this chapter, friction losses in pipe, or overall losses throughout your piping system. In chapter 3, we learn this Bernoulli's equation, which is in its perfect form. We assume that viscous effects are negligible. We say that this equation will work when there is no viscosity for the fluid. So we have fluid flowing from 1 to 2, there is no viscosity, it's perfect, and then this equation will balance from point 1 to point 2. That's what we assume in chapter 3. However, life is not so perfect. It means there will be some friction. You are going to start with high pressure, you are going to lose energy in the friction, you're going to end up with lower energy or lower pressure at this point. It means in order to work, in order to understand that friction, we have to modify this equation. Now to modify this equation, we change the format of this equation first. So what we do is we divide this equation by rho g. This term, this term, this term, all the terms by rho g. This is still same perfect equation, but only now it has a division with rho g, and it has different unit. Initially it has a unit of pressure, now it has unit of length. This is still same equation, and we are going to use this form of the equation throughout this chapter to modify and to do our calculation. So this is our Bernoulli's equation that we use to understand these losses in pipes. So we have a system. Let's say we have transport water from this point to this point, and throughout this system we have pipes, we have elbow, we have pump, we have T, we have another pipe, we have walls, and we have some joints there. Now if there are no losses, if everything is perfect, then the pump has to do less work, and then your Bernoulli's equation in its perfect form will be balanced. But in reality, there will be some friction here, there will be some energy loss here, 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 here. Everywhere there is some kind of obstruction or friction, you are going to lose some energy, and therefore pump has to overcome that energy to send fluid here from here. It means if you want to design this pump more efficiently, and if you have to design this system more efficiently, you need to know what are these losses. You have to have a way to calculate these losses. Otherwise, you won't be able to design a proper system, efficient system. So we need to understand that. So what happens? Very first thing, when it enters in the pipe, any fluid enters in the pipe and it's flowing. Let's say this is a cross section of the pipe, and this is the pipe wall, and here you are going to see there is very low velocity, and then you will get this kind of a velocity profile. This is called no slip condition. No slip condition, it means that the water here doesn't slip because of the friction, and then you will get this kind of velocity pattern here. Now why that happened? If we go through, look at details of the surface of the pipe, you will see something like this. Here either you will have rough wall or a smooth wall. Either way, you will have some surface roughness. You cannot have zero surface roughness, that's not possible. So here you have material with high surface roughness, you have material with low surface roughness. Either way, there will be some friction. Here you will have high friction, here you will have low friction. If this is the material, then you are going to need the pump, which has to overcome that energy, which has to overcome that high friction. It means that the power required by pump will be higher. In this case, power required by pump will be lower, but still it has to overcome some friction, and it has depend on this factor called epsilon. This epsilon is nothing but surface roughness of that material. So how rough is the material, that epsilon tells us. If it is more, high friction; if it is less, it's lower friction. And we have to understand that. So here, to modify this equation, to understand these losses, so all the losses we are going to have here, we are going to have some major loss and some minor loss. Major loss, we call it as a friction loss, and minor loss, we have called it as the losses due to kinetic energy in elbow, in pump, in wall, and other joints. So to understand that loss, we modify our equation like this. So this is our Bernoulli's equation from this point to this point. That's your original form. And then we add one more term, it's called head loss, and that's how we balance the equation from point 1 to point 2. So this is my point 1, point 2 here. If there is no friction, there are no losses, this equation should work in perfect form, but that's not the case. In reality, we have to balance it. By the time you reach here at this point, you are going to have some losses, and that's your head loss is balanced here. So this head loss is classified into two parts, something known as major loss and then something known as minor loss. A major loss is losses due to friction, and then minor loss is losses due to walls, fittings and bends. Friction loss is around 70-80%. Minor losses depend on how many walls and fittings and bends you have. So here, if you see in this figure, we have wall here, we have bend here, we have other fittings here. And because of that, you are going to lose some kinetic energy, and that's your minor loss. So our total head loss is a combination or a summation of these two losses, major loss and minor loss. Now, our objective is to calculate this head loss. We want to know how much head you are losing, or we want to know how much pressure we are losing throughout the process. So we have to have an expression for this head loss. Now this head loss is depend on pressure drop. If there is a flow from point 1 to point 2, you are going to lose some pressure because of the friction, and if we can calculate that pressure drop, we should be able to calculate head loss. So here we have point 1, we have point 2, and that pressure drop is depend on diameter, velocity, surface roughness, density and viscosity. So we are going to do here to Buckingham pi analysis to understand that pressure drop. And if you do that Buckingham pi analysis, what we get is these terms, pi 1, pi 2, pi 3 and pi 4. So this pressure drop is depend on these three terms, pi 2, pi 3 and pi 4. And if we can solve these terms, we should be able to get our pressure drop, and once we have pressure drop, we should be able to calculate head loss. So what I am going to do here, for these terms pi 1, pi 2, pi 3, pi 4, I am going to club these two terms together, Reynolds number and relative roughness. I am going to club them together. So here I am going to call it as friction factor is equal to phi Reynolds number epsilon by d. That's my relative roughness. Now these things does not have any dimensions, so keep that in mind. Reynolds number and surface roughness here, and I'm going to club them together. I'm going to rewrite my equation for pressure drop, which will look something like this. So this is my pi 1, L by d, I'm going to take it out of the bracket, and this is my surface, this is my friction factor here, function of Reynolds number and epsilon by d, and then I'll get pressure drop P1 minus P2 is equal to friction factor L by d, density V square by 2. That's the equation I'll get for pressure drop. Now I'm going to apply my Bernoulli's equation for this horizontal pipe from 1 to 2. Now as this is a horizontal pipe, and the area of cross section does not change from there to here, the velocity is going to stay same, so I'm going to cancel velocity. As it is horizontal, the elevation does not change, z1 is equal to z2, so I'm going to cancel that z1 and z2. So I have only three terms, this term, this term and this term, and this is the term I am interested in. I want to know what is head loss. Only thing at this moment I have is pressure drop P1 minus P2. So here I have P1, here I have P2, so I'm going to balance this equation. I'm going to rewrite this equation like this. P1 by rho g is equal to P2 by rho g is equal to plus HL. My objective is to calculate HL. So here I'm going to rewrite it for HL. HL is delta B by rho g. So now for this one I'm going to take this delta P and then I'm going to plug back in here. I'm going to rewrite it for delta P. So here for HL. So here FL by d rho v square by 2. If I put that in here and then if I rewrite the equation for HL, I will get something like this. HL major is FL by d v square by 2. Our objective is to calculate head loss, how much head we are losing, and this is the equation that we get. It means that we put the numbers in and then we will know how much head we are losing. Head loss is in meters or in feet, it's a unit of length. It will tell you that how many meters that you are losing throughout the process. If there is no losses, then you are losing 0 meter throughout the process. But as more losses increases, you are losing more head, and that's your head loss. If you have seen the video that was posted in your PowerPoints, then that guy loses 2 inches of head. So if you look at the video, you will understand that. So this is your head loss in meters. You want to know how much head you are going to lose, and that's how you can calculate friction L by d v square by 2g. Now, normally length of the pipe is given, diameter of the pipe is given, we can calculate velocity, flow rate is given, gravity is constant. What to do with this F, friction factor? What is this friction factor? If you remember, friction factor is combination of Reynolds number and epsilon by d. That's Reynolds number and relative roughness. Now, we have to have some number for that friction factor. Without the number, we can solve the problem. How to get that friction factor? To do that, we use this kind of chart. So in your book, or if you have it in the class, I have given you a page. In your book, you have this kind of a Moody chart. And for your exam, I'm going to bring some Moody chart in the class so that you will have it. How does this chart work? It is important for you to understand that. Now, this friction factor is function of Reynolds number and epsilon by d, and you need to know this friction factor to solve the problem here. So, what we have in this chart? If you look at left hand side, y-axis, we have friction factor here, we are interested in that. Then on x-axis, we have Reynolds number, and then y-axis right hand side, we will have epsilon by d. So our friction factor is a function of Reynolds number and epsilon by d. If you know these two things, you should be know friction factor is. And there was the guy, this Moody, and then he did a whole lot of research, and then he came up with this chart, and still today we use this chart to calculate friction factor. So how do we do this? How do we read this chart? First of all, you need to know Reynolds number. Reynolds number, let's say, and then this has an exponential place, 1,000, 10,000, 100,000, 1 million, 10 million. You need to know your Reynolds number. Once you know Reynolds number, you need to know epsilon by d. Epsilon is a property of material. It's called surface roughness. This epsilon is given in the book, given in the table. So you have to find out. So it is different for steel or wood or drawn tubing. You will get some value, and it has normally unit of millimeters. So it is important to calculate this epsilon by d. The diameter also has a unit of millimeters. So make sure that you get this surface roughness right. You get your Reynolds number right. So let's assume that your Reynolds number comes around 20,000. So 10,000 here, 20,000 here. So you mark here 20,000, and from that 20,000 you draw a line. So let's see if I can draw it here. So I'm going to draw a line from the 20,000 here like this, and then my surface roughness, let's say, come around 0.004. If that's the surface roughness, then that black line I'm going to follow. So this is the black line. I'm going to follow that black line, and then wherever we'll meet that black line, straight line from the Reynolds number, black line from my surface roughness, from that black line, I'm going to draw a horizontal. Let's see if I can do this. Okay. So the way it does is that you draw a horizontal, and then you mark a point, and that's your friction factor, and that's pretty much how it works. your Reynolds number, let's say it is 40,000. So this one is 40,000 mark. You draw a vertical, follow the black line from surface roughness, let's say it is 0.01. Then I'm going to follow this black line 0.01, wherever that meet I'm going to mark the point. From that point I'm going to draw a horizontal, and that will be my friction factor. It's very simple. And once you know friction factor, you should be able to solve the problem. So let's do some problems here. So what is the friction factor? It says 0.02 and the Reynolds number 30,000. So first of all, you have to locate where is 30,000. So here we have 10,000, 20,000, 30,000. So somewhere here between 20 and 40,000, we are going to have 30,000 here. And then it says 0.02. 0.02 is here. So first what I'm going to do is from 30,000 I'm going to draw a line which is going to straight like this. And then from 0.02 I'm going to follow that black line which will meet somewhere here. And then from that point I'm going to draw horizontal like this. And that will be my friction factor, which is around 0.05. So that's my first part. Then it says what is the friction factor for 0.004? 70,000 Reynolds number. So here first I'm going to locate 70,000. So my 70,000 will come here around 40, 60, 80, 70,000 somewhere here. So from that 70,000 I'm going to draw a line. And then 0.004. I'm going to look at here at 0.004. I'm going to follow the black line, and then wherever that my vertical and this black line from 0.004 meets, I'm going to mark a point somewhere here, and from that point I'm going to draw a horizontal, and then that will meet somewhere here 0.03, and that's my answer. Then for the third problem it says calculate surface roughness for 0.0004 220,000. Okay. First of all, locate your Reynolds number. So 220,000 is 100,000 here, 200,000 here, 400,000 here. So 220 somewhere in between. So 200,000. This is 300,000. That should be 250, and then so 220 somewhere here, just side. So now you have to guess really good. And then from here I'm going to draw my vertical, and then it says 0.0004. They have 3 zeros in front of 4. So my 3 zeros will come here, 0.004. Now I'm going to follow that black line. This is important. Don't draw horizontal here. You have to follow the black line. So if you follow this 0.004 black line, it goes up like this and it ends up somewhere here. So my combination of vertical and the black line from 0.0 black line from the 0.04 in this here, and from that I'm going to draw a horizontal towards left. So here I draw that horizontal, and then it will meet somewhere here, which is around closely 0.0185, and that's how this Moody chart works. This is very important for you to understand what is it. So here is 0.018 or 185. That's your number. Now if you in the exam, if you get 18 or 19 or 17, that is still fine, but you should not get very high number or very low number, somewhere in that vicinity. Then you will get almost right calculation. So make sure that you understand that. So that's for turbulent flow. If it is a laminar flow, then you can use simply this expression, F is equal to 64 by RE, and then you should be able to calculate the friction factor. But mostly you are going to end up with turbulent flow, so you have to use this chart. So that's how you can use Moody's chart. Make sure that you learn, you understand how to use this chart. Now in the class we did one problem. In this problem we have a drawn tubing. Drawn tubing like this. It is a very small steel tube like this one, and then high velocity air is going through 50 meters per second. We want to find out what is the air density, and we also want to know we want to find out what is the pressure drop, and we want to know what is the head loss, how much head you are losing throughout this pipe. And for that we have these two formulas. So everything else is given in the problem. We have length, we have diameter, we have velocity, we have gravity. Only thing we don't have is friction factor. And then you have to use Moody chart to calculate that friction factor. Once you know friction factor, you should be able to calculate pressure drop and you should be able to calculate head loss. So make sure that you read the problem, you understand the problem, and then you should be able to get that friction factor right. Now in this problem, very first thing for friction factor you need to do is to calculate Reynolds number. Reynolds number, you have velocity, density, viscosity, diameter. You can put the numbers in and you should be able to calculate Reynolds number, which will come around 13,700. It means now you have to use that 13,700 on the chart, and then you should be able to get this. You have to calculate epsilon by d. The epsilon for table 8.1, epsilon value for this drawn tubing is given. You have to use that value. Diameter is given, in millimeters is given. Calculate that epsilon by d, get your friction factor right. So here, get your Reynolds number, get your friction factor, get your epsilon by d, and then mark a horizontal, get your friction factor, and once you do that, you should be able to calculate delta P. So here, if you do your calculations, you have Reynolds number, you will get your epsilon by d is around 0.000375. So that's the number that you will get. And then you use Moody chart, and then from that you will get your friction factor as 0.028. So that's the friction factor you get, 0.028. And once you have that, you can use that friction factor here, and then you should be able to calculate pressure drop. And once you have pressure drop, use the same friction factor here, and you should be able to calculate head loss major, that's due to friction, and which is around 89 meters. So that much amount of head that you are using because of the friction, that's your problem. This is a solved problem from the book. Make sure that you do at home and then you understand what you are doing. So that's your friction loss in pipe. Apart from friction losses, there are some other losses known as minor loss. Minor loss is the losses, kinetic energy losses due to in walls, fittings and bends. So this one is the wall, these are some fittings here. So what happens is that when you have fluid flow, because of the wall, it will meet some obstruction. And as soon as it meets some obstruction, it's going to lose its kinetic energy. And that's your loss. As you lose kinetic energy, you are going to lose pressure. Now if you are using just one or two walls, pressure drop is not allowed. But if you are using multiple fittings, multiple walls, multiple obstructions, then those losses add up in that. So we need to know these minor losses too. And to know this minor loss, we have something known as loss coefficient. The way we have friction factor in major loss, we have loss coefficient KL to calculate pressure drop and head loss minor in the equation. So for pressure drop, we have KL 1/2 rho V square, and then we have KL V square by 2G, and that's your HL minor, and pressure drop due to minor loss, pressure drop due to wall. Now, how do we get this value of KL? Normally, value of KL is given in the problem. If not, there are tables in the book, you can find out value of KL. And once you use that value of KL, you should be able to calculate pressure drop, and you should be able to calculate minor loss. Now, if it is entering, let's say we have a large tank, and the fluid is entering in the pipe, in that case, the value of KL is given in the book. So we want to know pressure drop here, 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 and the head loss, then you need to know what is KL, what is loss coefficient. So here, in case of this kind of geometry, the KL is slightly higher, is around 0.8. If this is this kind of a geometry, the KL here is around 0.5, so here we have 0.5. If we have this kind of geometry, we have slight fillet here, the KL is 0.2, so it's lower. And then for this kind of geometry, the KL is lower. This is nice fillet, we have very limited friction and energy loss here, and therefore KL is 0.04. So that's the value of KL from the book we can use, and we can solve the problem if we have entry and entrance region flow. Then if it is exit, the KL value is normally taken as 1. So KL is equal to 1, 1, 1, 1. So KL is given as 1 because the entire kinetic energy of the exiting fluid is dissipated. So whatever fluid is coming in, the entire kinetic energy here is dissipating. Normally KL is taken just as unity or as 1 and you can solve the problem for exit. Again, it's given in the problem. If it's not, you can use the value from here. Apart from that, there are other losses with sudden contraction and sudden expansion. We have two pipes, let's say. One is a large pipe, another is a small pipe. They are meeting together. In that case, you are going to lose some kinetic energy. Or sudden expansion, small pipe and then large pipe. If that the case, then KL can be calculated by using this kind of graph. For that, you need to know the ratio of the areas. So in this case, you need to know A2 by A1. So let's say that A2 by A1 comes around 0.4. If that's the case, then all you have to do is that get that A2 by A1, draw a vertical. Wherever it will meet that black line, draw a horizontal from that black line. That should be your A2, that should be your KL. Now in this case it comes around 0.3. Now let's say your KL is 0.6, your A2 by A1 is 0.6. In that case, draw a vertical here, meet the black line here, draw a horizontal, and then it should come around 0.18, let's say. So that's how you can calculate the value of KL in case of sudden contraction. Sudden expansion is the same thing, we have different graph. Let's say if it is a 0.6, and this one will be your A1 by A2. So this one is A1, this is by A2. A1 by A2 comes 0.6. I'm going to draw a vertical, draw vertical to the black line. From the black line, I'm going to draw a horizontal. And if it comes here, then I'm going to say 0.18 or so. That will be my KL. So that's how these graphs work. And if there is a problem for sudden contraction and sudden expansion, you have to use this graph to get a value of KL. Once you have value of KL, you should be able to solve for pressure drop and you should be able to solve for minor loss. Other things such as elbows and bends and T's and walls, the value of KL is given. This is in the table 8.2 of your book. Use that value and you should be able to get the value here, and then you should be able to calculate KL, and that's how it works. So there is a problem. In this problem, what we do is that we use this table, and from the table we get the value of KL and we will solve it for pressure drop and head loss. So here we have a bend, we have an elbow. It says regular 90-degree threaded with an average velocity of 20 meters per second. Velocity is given. We have to calculate pressure drop. We have to calculate head loss. So how much head you are going to lose, how much pressure you are going to lose, we have to calculate that. For that, the formulas are given. All we need to know is value of KL. So here 1/2 rho v square. We have density. We have velocity 20. All we need to know is KL. And for that, we are going to use the table. So it says regular 90-degree threaded. So in the table, if you look at it, it says regular 90-degree threaded. The value is 1.5. So if you go through the table 8.2, it says elbows, regular 90-degree threaded, 1.5. All you have to do now, use the 1.5 here and calculate delta P and HL minor, which is come around 369 Pascal. So that's the pressure that you are losing from this point to this point. And then the total head that you are losing is around 30 meters. So 30 meters of head that you are usually losing, because that's your manometric head. If you have manometers at 0.1 and 0.2, the difference between two heights of the air will be 30 meters. So that's the importance here of this head loss. So 30 meters of head from this point and this point you are losing. And then you can calculate that by the value of KL using from the table, regular 90-degree threaded 1.5. If it is a different elbow, instead of regular 90-degree threaded, let's say it is long radius 90-degree threaded. If it is a different elbow, use different value. Long radius 90-degree threaded, you use 0.7. So all you do is that 0.7 here, do your calculations and then calculate pressure drop and HL, and that's how you do this calculation. All you need to know is how to use this table in the book. Once you have that, you should be able to calculate head loss and you should be able to calculate pressure drop, and that's pretty much the problem is. So that's how you get this pressure drops and head loss, major loss and minor losses by using different charts and different tables. So make sure that you learn them how to use. If you don't understand, hit me an email and I will explain it to you again, or set up an appointment with me and I will explain it to you how to use these charts and how to use these tables. So you need to learn those. Anyways, That's all for today. We will stop here. I'm going to put some practice problem. If you want, you can go ahead and solve this practice problem. This is not a homework, but that's pretty much it for today. So that's your chapter 8. There are a few other things that we will continue in chapter 8 in other classes. So that's pretty much it for the introduction of chapter 8. We'll stop here today and I'll continue with this the next time. Thank you and stay safe.